In this example, we want to sketch the graph of the rational function x squared divided by x squared minus 9. Now we're given the first and second derivatives for this function, and you should verify that you can do these by hand. You just have to use the quotient rule when you're differentiating. Now the first thing we want to do to graph this function is to find where f of x is increasing and decreasing. So we want to find where the derivative is positive and negative. So to do that, we first find where the derivative is 0 or does not exist. Now the derivative will equal 0 when the numerator is equal to 0. So setting 18x equal to 0, we get that x equals 0, of course. And the derivative does not exist when the denominator is equal to 0, and that's when x squared minus 9 is equal to 0. So x equals plus and minus 3. Notice if we put 3 in for x, we get 0, and negative 3, we get 0 in the denominator as well. So now we have to find where the derivative is positive and negative, so we'll use our sign pattern technique. And we'll pick some test values like 1, -1, 4, and -4. And notice that if we put -4 into the derivative function, we will get, now keep in mind we have a negative out here, we will get 18 times -4, that's going to be a negative number. This negative will make it positive. Now notice that the denominator is always positive because of this 2 right here, because of the square. So we don't really need to worry about the sign of the denominator. It's always positive. So in the numerator, we're going to get a negative number times a negative number, -4 up here. So that will make it positive. If we put -1 in for x, in the numerator we'll get a negative number times negative. That'll make it positive as well. So we're still positive here. Now if we put +1 into the derivative function, the numerator will now be positive, but we have that negative out here. Denominator is always positive, so we will be negative in here. And if we put 4 in, same thing. 18 times 4 is positive, but we have that negative out here, so negative. And this is where we are going to be increasing and decreasing. Remember, the pluses and minuses here represent the sign of f prime. So we see that we are increasing from -∞ to -3, and from -3 to 0. Notice I didn't write this as -∞ to 0 because our function up here, as we will see, has a vertical asymptote at -3. Notice if we put -3 in here for x, we get 9 divided by 0. -3 squared is 9 minus 9, that'll be 0. So we're actually going to have a vertical asymptote at -3, so we should not say we're increasing across a vertical asymptote. So that's why we left the increasing interval broken up as 2 separate integrals instead of just saying -∞ all the way up to 0. And decreasing is the same thing. We're going to go from 0 to 3, and then 3 to infinity. And same reasoning, we don't want to say we're decreasing from 0 to infinity because we have a vertical asymptote at 3. Let's identify any relative extrema. We see that we are increasing and then decreasing at 0, and so that is going to be where we have a relative maximum. Also notice 0, if we plug it into the function f, we do get a number back. It's not, f of x is defined as 0. So we will have a relative maximum at 0. F of 0, now if we put 0 into our function up here, we get back 0, right? So that's where we have a relative maximum. Now let's identify where our function is concave up and down. So the second thing, we need to look at the second derivative now, the sign of the second derivative. Let's notice our second derivative is 0 or does not exist. Let's see, the numerator is never equal to 0, right? X squared plus 3, that is never 0. The denominator, that does equal 0 when x is plus and minus 3 again. So that's where we're going to have critical numbers for f prime, where the second derivative is 0 or does not exist. So that's going to be, so f double prime does not exist at plus and minus 3. And it's not equal to 0 anywhere. We don't have to worry about it equaling 0 because the numerator is never 0. So let's do our sign pattern now for the second derivative, and we'll determine where the original function is concave up and down. And we'll pick some test points like 0 is a nice convenient number, 4 and -4. Notice how I try to keep the sign of the first derivative and the sign of the second derivative, the number lines lined up. So that way it makes it a little easier to graph the function. Now if we put -4 into the second derivative, you'll notice that the numerator is always positive, right? X squared plus 3, that's always positive. So we don't need to worry about the numerator changing sign. The denominator will change sign. If we put -4 in for x, we will get 16 minus 9, that's a positive number, cubed, so that will be positive. And the top is always positive. So we will be concave up from -infinity to -3. If we put 0 into x, the top will be a positive number. The bottom will be negative. We will get -9. 0 minus 9, that's -9 cubed. -9 cubed is a negative number. A negative number cubed is negative. So our function is concave down from -3 to 3. And then if we put +4 in here for x, we will get positive divided by positive. 16 minus 9 is positive. So concave up. And there, so now we know where our function is concave up and down. So we have concave up from -infinity to -3 and from 3 to infinity. And we are concave down from -3 to 3. There we go. Now let's identify any inflection points we have here. Well, we do see that we have a change in concavity occurring at -3. However, as we'll see, at -3 our function is not defined, right? That's actually going to be where we have a vertical asymptote. So -3 does not represent where we have an inflection point because the function is not defined at -3. The same thing at +3. We have a change in concavity, but our function is not defined at 3. So we don't have an inflection point there either. So we have no inflection points. Now let's identify any vertical asymptotes. Well, we see that the denominator we see the denominator here is equal to 0 at plus and minus 3, and at plus and minus 3 the numerator is 9. So we're going to have a vertical asymptote at plus and minus 3, so that's going to be at negative 3 and x equals positive 3. Those are the vertical asymptotes. And let's see about any horizontal asymptotes. Well, let's notice that the limit as x approaches infinity of by our rules for limits at infinity, the degree of the top is the same as that of the bottom, x squared and x squared, so the limit as we approach positive or negative infinity is going to be the quotient of the leading coefficients, which in this case are 1 and 1, and so this limit is going to be 1. And that's true for negative infinity as well, so we could just write here plus or minus infinity. So we have a horizontal asymptote of y equaling 1. That's our horizontal asymptote. And here are the vertical asymptotes up here. Now let's note any x and y-intercepts. Well, our y-intercept, that's easy enough to find. If we put 0 in here for x, f of 0 will be 0 divided by negative 9, so that is 0. So that's where we're crossing the y-axis. And any x-intercepts, well, that we would obtain by setting the numerator equal to 0. So we would set x squared equal to 0. Well, of course, we get back 0 there. So those are the values where we're crossing the x-axis. So it just so happens that our x and y-intercepts are the same. And if you want to, you can write these as coordinate points as well. This would be 0, 0. That's the point on the y-axis. And down here, the same thing, 0, 0. Putting 0 in for y and solving for the x's, well, we just got back 0 for the x. Now we can sketch the graph of this function. So let's notice all of our information up here. We've got a relative maximum at 0, 0. Let's plot that right here. We have vertical asymptotes at plus and minus 3. Let's sketch those. So let's say 1, 2, negative 3, 1, 2, negative 3. So we have vertical asymptotes occurring here and here. So that's at 3 and negative 3. We have a horizontal asymptote of y equals 1, so let's put that in here, right here. So there's a horizontal asymptote. Now we can start sketching the graph of our function. Oh, notice the x and y-intercepts are 0, 0, and we already have that point there. That's actually a relative maximum. So now, let's see, if we go from negative infinity to negative 3, our function has to be increasing as we get towards negative 3 and concave up. This is a horizontal asymptote, so it has to hug this line out here, this dotted line, and as we come towards a vertical asymptote here, we're either going to break up or break down. Well, we have to stay increasing and we have to be concave up, so we are going to have to break upward. So that's what the graph of our function is going to look like on that piece. Now, as we go from our vertical asymptote towards this point, we either have to come down like this or come up towards that point. Well, as we go from negative 3 to 0, negative 3 to 0, we should be increasing, and negative 3 to 0, we should be concave down. So the only way we can do that is if our graph goes like this. And now we have a relative maximum right here. Now our graph is either going to have to go up towards the vertical asymptote like that, or down like this. Well, it's a maximum here, so we should break down. Let's also note from the sign of f prime, we see that we should be decreasing and concave down. So we have to go like this, break down towards negative infinity at this vertical asymptote here. Now as we go from 3 to infinity, we should be decreasing and concave up. Well, the only way we're going to be decreasing from this vertical asymptote is if we come down from positive infinity, and then we have to hug that line. So we have to come down, remain concave up, and then start getting close to that dotted line. And there, that's what the graph of our function looks like. Let's take note of the graph that we have from graphing it on a computer graphing system and see if it matches up with this information that we have here. And so here's what our graph looks like by graphing it on a computer graphing system. Notice that right here we have our vertical asymptotes at -3 and +3. We have a horizontal asymptote at 1. We have a relative maximum right there at 0, 0, and that's also our x and y intercepts. And notice how our graph hugs the dotted line, increases to infinity as we approach the vertical asymptote. Then we jump over the vertical asymptote, come up from negative infinity, approach 0, 0, drop back down, and then crossing over this vertical asymptote, we come down from infinity and remain concave up as we go towards positive infinity and hug the horizontal asymptote. So this looks exactly like what we had graphed. So that verifies what we did.